Well, welcome everyone. If you could please take your seats, we'll go ahead and get started. My name is Chris Barkin, and I want to welcome all of you to the William W. Hay Railroad Engineering Seminar here at the University of Illinois. Before I introduce our speaker, we have a few housekeeping items I'd like to take care of. Of course, the usual one is please turn off your cell phones so that they don't ring during the presentation. I think mine's already off. If we have a fire alarm, please exit from the doors on either side of the room and then descend by the stairway to the first floor and exit the building by the doors at the base of the stairs. And let's plan to carefully cross Main Street and gather on the north side of the street. And let's use the buddy system, so please note who's next to you and make sure that they get out safely. If you haven't already swiped in, we'll be passing around the attendance sheet. Please be sure to sign in for that, because we need to keep a record of who's attending this seminar. And also, if you did not receive a direct email announcement about this seminar but would like to be on our list, please jot your name down and your email address legibly so that we can include you on future announcements. I'd like to welcome those of you who are joining us by telephone, and that includes representatives from RK&K, Patrick Engineering, BNSF Railway, GREX, Harsco, Vossloh, TUV Rail Sciences, URS, Michigan Tech University, Railstar Engineering, and the Federal Railroad Administration. And those of you who are dialing in, if you wish to receive continuing education units for your participation, please send LB Fry an email with your information as described in the email announcement. I'd also like to ask our speaker if you could please, when you get questions from the audience, repeat them for the benefit of the people dialing in so they can hear. Is Matt Grieve here? Ah, there's our representative. Okay, thanks, Gio. The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank the U.S. Department of Transportation for their ongoing support. It is greatly appreciated by those of us here on campus, as well as those participating via the internet. Over the past decade, much broader appreciation has developed of the importance of track support conditions to a safe and efficient railroad bed. This has become especially evident as axle loads, traffic volume, and speeds have all increased. One of the leaders in developing this new understanding is our speaker today, who's been working with the railroad industry on this topic for decades. As he'll discuss, effective roadbed support requires balancing design factors such as layer thicknesses and material properties to achieve desired roadbed structural support and drainage, while at the same time maintaining reliable performance and minimizing traffic disruptions and maintenance cycles. Professor Jerry Rose has been in the Department of Civil and Environmental Engineering at the University of Kentucky since 1971 in the areas of materials, transportation, and construction. He is a native Kentuckian and a civil engineering graduate of the University of Kentucky and Texas A&M University. He's a registered professional engineer and a member of several technical societies, including the ASCE and ARIMA. And I should say that under Professor Rose's leadership, Kentucky was among the first, if not the first, U.S. universities to initiate what's become a national renaissance in railway engineering education at U.S. colleges and universities. For my part, his was the first curriculum I consulted after I arrived here in Illinois in 1998, and I initiated a correspondence with him, beginning a friendship that continues to this day. Professor Rose has been the principal or a co-principal investigator on 23 research projects culminating in 134 technical publications and 97 technical presentations to conferences. He has supervised the research projects of 35 graduate students in railway engineering. His contributions to the design, evaluation, and use of asphalt for railway track beds are widely recognized and appreciated by both the national and international railway engineering community, and have served as catalysts for numerous applications on some of the heaviest tonnage and highest speed rail lines in the world. Please join me in welcoming our speaker today, Professor Jerry Rose, who will present the William Hay Railroad Engineering Seminar entitled Maintaining Adequate Track Bed Structural Support, an Important Railway Infrastructure Issue. Thank you.
I'm turned on, I believe. Okay, very good. Thank you very much, Chris. I certainly do appreciate the opportunity to be here today and participate in the Hay seminar series. I've had quite a whirlwind past 24 hours. I've listened to, I believe, 8 or 10 graduate students give abbreviated presentations on their research work, which is very, very interesting. Also, this morning, talked with several professors, and also this morning toured the research facility out north of town with the pilot size, or actually full size, track bed for research studies. And actually, on the way up here, I met Professor Stark and one of his students, and we spent most of Wednesday on CSX's main line just north of Evansville, Indiana, taking some track bed response tests. And believe it or not, in a little over 4 hours, we had 8 trains, which is good from the standpoint of getting a lot of data in a short period of time, but is representative of some of the tonnages and trains that the railroads are accommodating today. In fact, we got intermodal trains, got grain trains, we got coal trains, we got auto trains, and I think a few mixed freight train thrown in. So that was very interesting too, to participate in that. I remember my first visit to the University of Illinois, and actually it was in May of 1982. And I was here to actually attend a 2-week short course that was taught over in the Talbot Laboratory, and by none other than Professor Hay. And he had provided this service for a number of years to the railroad industry. Normally the companies would send their employees in the engineering department that they thought had some upside potential, and so they would send them to his course to get jump-started a little bit more on some of the technical aspects of the track and other issues. So that was a very good experience that I had. And actually, the second edition of Hay's textbook, which most of you are familiar with, came out during that course. We were supposed to have it at the start. It came out in the middle of it, so we had it for the second week. And I asked him, or I advised him, my colleague had been an office mate of Professor Hay when he was a student, later professor at the University of Illinois over in Engineering Hall on the 3rd floor there. And so he had tipped me off about Professor Hay and what some of the possibilities were. And I advised him that I had planned the following spring to resurrect a long dormant 25-year railroad engineering class, and that I would like to attend his course to sort of jumpstart me as well. So I was able to obtain a seat there for 2 weeks. And so I asked him to, if he would, to autograph my textbook. Now, this was $37.50 was the bookstore price. I should have bought several for investment, but I didn't. But so I've always appreciated, I added the date to it there, but I've always appreciated his, and it's really unfortunate in some respect for you young folks to not have had the opportunity to meet him, because not only was he a nice fellow, nice person, but he was a very interesting person to talk to, and a lot of that was based on his experience, which he had done about everything you can imagine in the railroad industry, in the engineering side. And he was, quite an inspiration to many people. He sort of kept the torch burning. As you know, in the 1950s and 60s, the railroads were pretty well on a downswing, at least in hiring engineering folks. And but in the 70s and 80s, with the 3R Act and the 4R Act and staggers and so forth, he also saw the upswing, which we're still in, and of the industry. So that was his contribution there. But with him, the railroad industry was number one, and you weren't with him very long until you realized that. Okay, my topic today, as you see here, this is going to be a little bit different from most of the Hay seminars. Most of those are fairly narrow topic that's developed in great detail, theoretically and experimentally or whatever. And I'm going to cover several areas. At the end, I hope to bring all of this together, and we'll have a few concluding remarks to do that. How well I'm able to accomplish this, I'm not sure. I hope game day is a little bit better than the last practice. I wasn't too well satisfied, so we'll see what happens that. But my enemy is the time, so I hope I have a time to go into this to the detail that I want to. So this is it, and we're going to start back in the 1800s here with the evolution theory. Initially, railroads in this country were pretty well just built on the natural ground, and if you were in an area that had fairly stable soils, the more granular soils, probably the performance was a little bit better. If you're in the clay soils, probably not so. The performance is probably not so good, particularly in the wet weather. But our track bed system for most of the mileage in this country really developed, of course, in the 1800s. Well before the highway industry. Highway industry really technically didn't develop very much to around 1910 in the teens. So really up until that time, the railroads were, of course, the dominant form of transportation and led in the development of these sorts of things. So basically the track was laid on the natural ground, and that's pretty well what you had. Then later came ballast rock, and it was pretty obvious that if they would add some more granular material, ballast-sized materials in and around the ties and under the ties, and give a little bit of attention to drainage with ditches and so forth, that they would get even better performance. And so we're evolving here. And so the all-granular track bed, road bed, pretty well evolved from that, from some of the early pictures of that. And certainly today is by far the most prominent type of track structure that exists in this country and most other countries. Of course, a lot of advancements have been made. Cleaner steel, bigger rail, better rail, plus concrete steel, other types of ties, improvements in fasteners, other track materials, and all of that, as the industry has increased. Still, the problem of drainage exists. Typically, been said the three major problems is with track is drainage. It's interesting. I read an article in the 1927 issue of the L&N Employees magazine. This was written by a roadmaster, and it was titled "The Importance of Track Drainage." And his basic premise of the presentation of the article was that he says if we can maintain a hard pan, we can hold the track. Now, that was the terminology at that time. I think what he was saying was that we can maintain the geometry to the level that we need to maintain it if we have proper support or a hard pan within the track structure. Obviously, drainage assists in doing that, but the key really is support and providing the necessary drainage to make sure that that support is that. And some of these are extremes, just to make a point, but periodically these things do happen. And you get surface problems, cross level, track settles, pumps out. Obviously, if all this material pumps out, track has to drop. And maybe you get cross level problems as well as surface problems. And then profiles develop, and wear and tear of the ties, the abrasion of the ballast and the ties, and so forth increases as well. That you don't want, obviously, from that standpoint. And these are not typical. They are prevalent necessarily, but occasionally they do occur. And just an example here on a road crossing, the one on the left looks pretty bad. That picture was taken several years ago. But on the right, this crossing for the driver is just as rough as that one that doesn't look so good. And I think as you can tell, you can actually see here on the right, you can, I hope I get this, oh, that was not what I wanted. The pointer's up at the top. At the bottom. It is not this. Oh, that's it. Okay, thanks. You can see the tension crack here where the settlement has occurred. So this is settled, And, you know, that's just as rough, really, as that one, although it looks better. But the problem here is settlement. There's no question about it, due to the truck loadings and the rail loadings and so forth to do that. So as you all know, the solution to all this is to come out and surface the track, add ballast, adjust the ballast. You're really adjusting the geometry to bring it back to within the requirements that are prescribed for that particular class of track. And that's the process that's repeated over and over where you need that type of thing, and you bring the tampers out and consolidate and pull and push and so forth until you get the track back to the required geometry. All right, the idealized track cross-section would look something like this, which you have the components, the ballast, subgrade, and typically they're designed to be economical and easy to maintain. That's certainly desirable attributes. What the railroads are doing are constantly evaluating alternatives. Normally these alternatives are more expensive, and then the question is whether or not the additional costs are justified. That's generally the bottom line in the final analysis, and how much interference from operations are required for various different solutions to certain problems to do that. Basic requirements, of course, it's a guideway and support the loadings, and if you have a good quality track that maintains the geometry that is required for that class of track, then all these other things will be dictated by that track quality. And those are the ABCs of what you want. It dictates the permissible wheel loadings, which is pretty well set. Safe speed, trying to maintain the geometry over a period of time to minimize the amount of maintenance that has to be done. The overall safety is tied to speed and the dependability and efficiency of operations due to track work that inhibits, obviously, train operations. So all of those are ultimately dictated by the quality of the track and how well it maintains its geometric features to do that. And whether or not you've got a Class 1 track or you've got a Class 4 on up to Class 9 will be dictated by the safe speed for those particular geometric features that do that. So that's the way it goes. Now, talk a little bit about the track functions. I have a number of notes here, which I always forget to look at, make sure I don't leave out anything. But let's talk a little bit about the track functions, and then we'll get down to the track bed. Basically, maintain vehicles on a fixed guideway, provide a high level of vehicle ride quality, and withstand and distribute the loadings, as we've talked about. In this country, typically that's a 36-ton axle load that has to be accommodated, plus whatever dynamics that we have. Now, the track bed road bed is a little bit different. This is a system. You have three materials here, primarily, that support the track in the imposed loadings, and they all have certain characteristics that they have to impart to the track structure, and we're going to talk about each of those just very briefly here as we go into those. Actually, I like this picture. I actually got this from some notes, I think, from the University of Illinois, and I added some over in the red, but the components do not function independently, basically. It's a system, and each layer is designed, for instance, the ballast to protect the subballast to protect the subgrade, basically is what it is. And each component contributes certain attributes to the track, and it is a system. It has to be analyzed as a system. For instance, the ballast, what we're mainly interested in, what I'm concerned about here is distribute the loadings with decreased unit pressures down to the subballast, as well as support the track, and my definition of track is the ties and the rail. Then you get down to the track bed and the road bed, and it serves to drain the track. And then these other three are very, very important also, not necessarily from a structural standpoint, but they're desirable attributes. So, and it's got to be adjustable so you can move around to adjust the geometry. So ballast is a very, very important, serves many, many purposes. Then the subballast, a little bit different, more like a highway base mix, as you know, fairly watertight, it will compact very tight, dense. Now it supports and confines the ballast. So we got this confinement term here. We'll talk more about that later. Distributes the loadings to the subgrade with diminished unit pressure, hopefully within the bearing capacity of the subgrade. It's a separator and a waterproofer. So it has some very, very important attributes or characteristics as well. Then the subgrade then supports and distributes the loads imposed by the subballast and confines the subballast. We got this confinement term again here. Facilitates drainage, hopefully to keep water from saturating and soaking, and as a working platform for that. So each of these materials and layers has several different attributes to do that. Of course, just a little bit more on the subgrade. Fairly simple, borrow a lot from the highway industry as well, but typical soils, geotechnical technology is used. Soils vary a lot, the native soils where you are, and they have to be considered. And you have to evaluate, maybe stabilize, and certainly the top 2 feet would be the most important, where the pressures are the highest, just below the subballast. So subgrade's important too, and it has certain characteristics to apply. Now we're going to change here a little bit. We'll get into structural design very briefly of tracks, and we'll discuss one that I'm fairly familiar with. What we started with was basically a trial and error type thing. We start on natural soil, we add some ballast, we get better performance, and so forth. That's trial and error based on experience. Then once you get enough of that experience, at some point this sort of leads into an empirical design based on past experiences, trial and error, and so forth. And then maybe we come on up and get some measurements. We actually go out in the track, get some measurements to sort of confirm what some of our trial and error results have been. Maybe take into consideration materials property. And now we're getting into a pure empirical and maybe bordering on a rational method of design. And then if we have a program where we can actually calculate the stresses and strains at different interfaces and so forth, then we do have a rational method. And ideally, we can blend this rational measurements and calculations actually back into measurements, and then we've got a proved rational program, which is as good as what, which is the ideal situation to have. Track design is actually contained in Chapter 1 of the REMA manual, Roadway and Ballast, and it's largely based on the Talbot method, which was developed here by the University of Illinois. Back in between 1918 and 1940, Talbot and his committee, it was a combined ASCE-AREA at that time committee, and they studied trackbed designs. They instrumented many track sections with all kinds of levers and dial gauges and everything else they had at that time. Of course, greatly preceded computers or anything like that. But at any rate, they came up with some findings. We're going to discuss those very briefly here. But obviously, from a pressure distribution, now we're going to talk about stiffness just in a minute, but we'll cover pressure distribution. Two different things, totally different, really, in their application. But at any rate, obviously, you must determine the allowable loads, like in any other structure, what the actual will be, and you compare and adjust, and then you either make them stronger, you make them larger, whatever the units are, the layers or the members or what have you, considering the materials properties and thicknesses and so forth, and make a structural design. Well, that can be done in track beds. We're going to talk about that a little bit. As I said, most of that was done early on by Talbot and his committee, and they idealized these beam-on elastic foundation type systems. And then since that time, there are some computer systems, combination of finite element layer elastic analysis that have been developed to analyze track beds as well, very similar as in highway industry. And these rely very heavily on geotechnical pavement design principles. You get into layer design, primary reason being that the highway people have been in this business for many years in research, and a lot of that can be borrowed, as we're going to talk about. This is sort of the overriding equation that came out of the Talbot work, and it was an empirical equation that related the pressure at the subgrade, which is P sub C down here, which would be on the subgrade right here, the vertical compressive stress, as a function of the pressure P sub A directly under the tie, and the thickness of the ballast, which would be probably a combined here, and those were the relationships. So if you had a limiting value here for subgrade, and you could calculate what, for the subgrade, you could calculate what this load was based on the wheel load and the impact under the tie, then you could relate those two, and basically the the thicker section, which would be a thicker ballast section. I've never known why they called it H rather than T, but that's what they did. Then basically your only option is to increase your granular layer thickness is basically the design. Of course, obviously you dig into a lot of track beds, you don't have a layered system. It is a mixture of ballast, degraded ballast, soil, coal, you name it. It's in the existing track. But now keep in mind these tracks evolved over a period of years. They were not designed. Now they're not all nearly this extreme, but they can be. But irregardless, even if you have a ballast for a short distance and then it gradually degrades or becomes finer and finer, it's hard to get the absolute separation here in order to analyze this from a rational method. You really can't do it. And that's the main reason why it hasn't been done very much in the past from that standpoint. This is basically just a little more detail on that, and I won't spend here for just a second, but really what it says is, and I'm sure those of you who have had the track design course here, you've gone into this, but on a given tie, you're going to have two wheel loads, and you convert those to a dynamic loading, which basically is a function of the speed, the way the system's set up. And you divide that, you assume that 2/3 the bottom of the tie is in bearing, and then about 40% of that load is going to be on that one tie, and the other 60% distributed on another 8 or 10 ties either side. So basically, and so you assume 40%, and typically guidelines are that it should be less than 65 psi, or 85 for concrete ties. And generally, for a given wheel load, 36,000 pounds, it'll come out very close to 65. Okay, then you plug that in the equation here, and you calculate a P sub C, and typically, which is really sort of like the bearing capacity, should be less than about 20 psi. Be an unconfined compression strength somewhere around 8 psi. So that's the typical design criteria, and it's been adjusted a little bit that is used. And this is right out of the REMA. You can't read that, but that's right out of the REMA book on that, chapter 1. And basically, this is generally used to calculate an H for a given P sub C and P sub A. Typically, it comes out about 2 feet. So what it says, most any track bed on that type of soil, you need at least 2 feet of granular material below the tie, whether that's mixed 12 and 12 or whatever, that would be it. So that's pretty well the design based on that system. Now, stiffness, a little bit different. Now here we're calculating stresses in this other system, and that's one way of design. The other one is designed based on stiffness, limiting deflections. To do that, and typically a good quality track is going to have you want to keep deflections to a minimum for many, many reasons, and primarily for wear of the track components and this sort of thing, and that's always defined as the modulus, the track modulus, to do that. And those values are well known, what a typical track, wood tie, concrete track, what a good modulus or a satisfactory modulus would be. And of course, that's what you basically have as the empty load travels along, or the loaded load. This is just a moving deflection is all it is, from 100 miles or whatever. Every wheel is a moving deflection that goes through there. And based on what this deflection is as a function of this wheel load, then the modulus can be calculated. And of course, that one's pretty simple to do. Now, there are some rational methods that are available. This happens to be the one that I'm most familiar with, is Kintrack. This was developed at the University of Kentucky many years ago. It's been through several iterations since that time, actually back in the old Fortran. But, and it incorporates a good bit of highway design, and particularly the failure criteria. Now, of course, in these programs, one thing is to calculate stresses and strains at different interfaces. The other thing then is to be able to predict service life, or useful life of the system. So this is designed based on Kin Layer, which is the flexible pavement design system that has been used for that. And I'll give you just a little bit of background on this, but it has 2 steps. One is to calculate stresses and strains, as I mentioned, and then predict the design lives that based on highway failure criteria. We don't have railroad failure criteria, but basically after you get down through the ballast in particular, you got a layered system down there. It behaves pretty much like a highway would down in the highway structure as well. So that's really what we have used. And it's good for unbound elastic layers, the typical all-granular track bed, ballast, subballast, and subgrade, and or other layers can be put in there or substituted with various different properties, even if they're elastic and viscous as well, if you have the failure criteria for those, and that's what we use. And actually, we use three different types of track beds. This is the typical all-granular, ballast, subballast, all-granular, non-bound material. And then the underlayment is a substitution of asphalt for the granular subballast, and then the combination is a combination of both the asphalt as well as a granular subballast on the subgrade. And this is the system that's used. So it's available for these or many other. And the failure criteria then is to add up the number of load applications to failure based on the subgrade, which would be the compressive stress, which you convert from strain to stress, since that's used more in railroads than the elastic modulus of the soil. And then on the asphalt, it's the resilient modulus and the strain at the bottom of the asphalt layer. So we're talking about here vertical compressive stress on the subgrade and failure of the asphalt, about tension in the bottom. And then you sub up all of these and determine what the design life, service life or design life would be. And I'm just going to give one example of this. You can obviously run sensitivity analysis, vary one variable, see what the effect is on the other. And this is subgrade modulus, the effect of subgrade modulus on the vertical compressive stress on the subgrade. And actually, as the modulus increases, this is a pretty strong subgrade, the pressure on the subgrade actually increases slightly, and by theory that should happen on mechanics. But it's still very low. These pressures here are very, very low, the 10 on up to maybe 15 or so PSI. So we're talking about some very low pressures. However, if you put that in the KinTrack program, based on kin layer failure from highway pavements down in the layer elastics, when you analyze the subgrade service life for these four situations here, the life increases. In other words, although the stress here is slightly higher, the predicted life is multitudes of times higher, because being a stronger subgrade, it'll take much higher, many more applications of a higher subgrade stress, and as far as the predicted life. So these are the sorts of things that a program like that permits the designer to do in analyzing that from that standpoint. So that's all I have time to cover on that, but that gives you. And actually, of those pressures on top of these are pressures on top of the asphalt. This is based on some of our research. And you can remember this. We're going to get in some European practice here in a few minutes. And you can remember this 15 PSI. Now, this is on top of the asphalt below the ballast for a typical four-axle, 380,000 pound locomotive, six-axle, 15 PSI. These are unloaded cars with a flat wheel thrown in there. But at any rate, those are some of the values that you can expect. Actually, that was on some CSX tractors down in Kentucky. This was out at TTCI. Very similar type structures out there, and these were the pressures under the locomotives at the top of the asphalt layer, about 15 PSI, and these were under the 310-pound cars that they dragged behind those test trains out there, a little bit heavier and a little bit higher pressure too. And this was on the subgrade below, so we're down in the range of 7, 8, 9, 10 PSI in those ranges. You'll see some test data in a moment from Europe. Now, they're much lighter loadings, and those are going to be down in the 2 or 3 PSI range under the loadings over there, the high-speed passenger train type loading. So it gives actually, we've done a little bit of comparing, I hope you can see this, of what we call the KinTrack predictive values, that's from the program, versus the InTrack data, ITD, which is this. And this is a 10 over 5, be 10 inches of ballast over 5 inches of asphalt. Kintrack predicted 21 psi. We measured 16. You see, we're back to this 15 or 16 again. Here was a little different section, 22 and 15. Out at TTCI, they predicted that's a 12 over 4, 12 inches of ballast over 4 inches of asphalt, thinner section, 11 to 14, and this one's 21 to so still not too terribly bad for an 8 over 8. These are the pressures down on the subgrade, which they had pressure cells installed on the subgrade, and they agree very closely with the predicted value. So that's a program that really is sort of proven. You can actually prove it then if you have the empirical measurements to back into the predicted values from the program. And so that's just an example of some of those I thought I'd show you. All right. Last thing is I'm going to deal with some international applications. I'm going to concentrate on 3 today. That's pretty much all I have time. Some Italy, France, and Austria. So those are the 3 that we'll concentrate on. And some of now this is going to concentrate to a great extent on the use of asphalt in addition to granular material. And a lot of the research over there nowadays is concentrated in that area. So that's what we're, and some of this information is actually is as new as the last month because I was able to obtain some very recent information, and that is interground in here. So I'm going to concentrate on that for that. Italy has widely utilized asphalt and structural design on their high-speed lines now for a number of years. Rome to Florence was one of the first ones that was done way back in the 1980s, primarily on that. And since that time, it's been used on numerous others. These were some of the research findings back in 2000 and translated into some of their findings from this type of trackbed construction. This term gradually, I think what they mean here, asphalt is a viscoelastic material, and the vibrations and the pressure distributions are basically a little bit different from a purely elastic type material. So that probably is what this gradually means. It's not a real fast application. Now this is a typical cross section they use, and I want to point out a couple of things here, which I think is interesting. One is what they do, they actually define the strength or stiffness properties, of their layers to accommodate their loadings. In other words, this is a ballast section here, 35 centimeters of ballast on about 12 centimeters of asphalt, and this is probably this is a modulus value for the asphalt, 200 megapascals. This is their super compacto mix underneath there, which is probably a subballast or certainly a very much improved soil, and which is 80. And the embankment, which we probably call somewhere here you got a subgrade, maybe they just call it that, 40 megapascal. So the basic difference here is they actually quantify the stiffness values for the various different layers, and then they design their system to accommodate that. Okay, and you're going to see some more of that. These are just some construction views over there of some of their activities. Now this is a little bit later in 2008. Here was some more findings from a research report from the structural liability, whatever that is, increased modulus and uniformity. This uniformity is very important, I think, and they also use it's a homogeneous stiffness or support, and I think that's important too. Any track bed that's very consistent in support, basically that's important. They've gone into life cycle cost, reduced ballast fouling, vibration levels. Again, what do we have? A layer of a viscoelastic material that attenuates vibrations at a different level than an all granular material. And then the total thickness of the section is a good deal less than the all granular traditional type system. So these are some findings from a couple of publications in the 2000s. And a couple of more construction slides over here. I actually use which I thought was interesting, a falling weight deflectometer to assess the structural competency of the roadbed or what have you. And one they're finished over here too. So that's some of the work in Italy. Now France, a little bit newer work, but very, very detailed work. In fact, the French were over here summer before last. In fact, I heard their presentation on some of the research work that they're doing over there. One of the first ones was the Paris to Strasbourg high-speed line. This was sort of a research project, and 3 kilometers of asphalt subballast was used on that line. Actually, at that time, I think this was 2009 maybe, when they ran this was at one time the record-breaking speed for rail on rail. It's been eclipsed since then, but it's still on the YouTube. It's just a blur, obviously. I mean, you can watch it, but yes, sir.
I'll wager it's the fastest train on ballasted track.
Okay, you could very well be true. The fastest train on ballasted track. Okay, yeah, that's probably true. But at any rate, that was part of the history of that, to do that. This was the test area up there that they did. They they inserted temperature sensors, accelerometers on the sleepers, strain gauges on the asphalt and so forth, and then pressure cells on the subgrade to monitor these over a number of years. And I've got some test results here we're going to look at, some of which are brand new. This was the section that they had on the right here. It's a good deal thinner than the classic all granular typical section that they have. This is a layer of asphalt. They call it bitumen still, but that's it there. And then a super subballast, and then on down on the embankment type material. And this is just a cutaway of some of their instrumentation. It's very heavily instrumented, not only the asphalt section, but obviously the classic section as well, the all granular section. So this gives you an idea of some of the testing. And this was, again, just some of the construction views there of this. And you can see the different layers here on the right where they stepped them in as they went up to the track, and some of the construction views as well. And these are just comparing the sort of traditional all granular section over here with the asphalt section here, and some of their you'll notice this data down here for the 80 megapascals, very similar to the Italy test. So these were the testing we've already gone over. Now this testing has extended past 2011. And these are some of the findings for that. And this is this year's reports here. But at any rate, the economies of materials, thinner section, can drive on it, lay track on it regardless of the weather during the period once you get the asphalt down. Increased stability of the structure, reduction in maintenance efforts. I'll show you some data on that in just a minute. And control of vibration. I think that's generally, again, due to this viscoelastic layer in there from the vibration standpoint. And some of the high axle loads, high speed, and so forth and so on. So at any rate, this is some of their data now on pressures, ground pressure. So this would be down on the subgrade, I think, below the asphalt. And you'll see on the test zone, which is the asphalt section here, we're talking about 10 kilopascals. I think that, and these are at different dates. These come on up through 2009, 7 to 9. And that's about 2 psi, as I recall, 2 to 3 psi. It's very, very low. I'm exerting about 6 under my feet here as I stand here, 210-pound person. But then on the classic structure, you'll see those pressures are higher. They're still reasonably low, but keep in mind these are lighter weight wheel loads on these high-speed passenger trains over there. But that's sort of the relative measures of those from that. And as they say, approximately 50% more low than in the classic structure, and that's where they're getting that. So this is some of the data that backs that up. And then also, this is, I think, probably one of the more interesting I've ever seen. This really should be down here, and this should be up here. But this is degradation of maintenance, whatever that is, geometry or whatever. And here they required some maintenance. And this is the rate at which it degrades. This is the classic structure. And then they do maintenance, and then it starts degrading again pretty well on the same slope. The bituminous is at a much slower rate, and then perform the maintenance, which is probably surfacing, and then it pretty well levels out. So that's some maintenance data. We don't have units, but basically bituminous, more slow rate of degradation. Now remember, these are, this is just translated. Best effectiveness of maintenance work. In other words, what they do does the job, I guess is what they're saying. And attenuation of slope after, I don't know what jam is. Maybe we have someone who knows that. But at any rate, that's the first type of data that I've seen of that type that's been produced out of there. And these were some more comments from Robinette last summer when he was here. And they basically, pressures about 1/2, and that's still the case. Deflections are 1/3 of the allowable, so reducing track deflection. Sleeper acceleration is not affected. In other words, it's not a whole lot stiffer, but it's stiff enough, I think is what they're saying. Less maintenance required, and I showed you the data for that. And the track performs well, whatever they base that on. And then last month, these are some of the final findings, at least, of their report that has just come out on that. And so these are just firmer confirmation of some of those comments. All right. And then these are the other track sections that are presently under construction. Some of you may be familiar with France, and you know where some of those are. I'm not. But at any rate, these are the others that are scattered around that are presently under construction, based on the research findings on the one that we just talked about up here as well. So, and they're also looking at two different designs. This is the unbound granular material, which is the typical subballast, and this is a treated soil that apparently they can increase the quality and bearing capacity of this to equal probably this. So we have an alternate design for that. And then the last one is the Austrian railways, and this is pretty brief. But, of course, that's a small country. But they have been implementing asphalt layers for a number of years, going back to the 1970s, as you'll see here. And these are some of the advantages that they point out: the drainage effect, void pumping, and again, you get back to this homogeneous and providing a consistent load carrying capability for the track. And what really that does in the final analysis is there's less of this galloping as you hit soft and hard spots and soft and hard spots. So you eliminate that, so you get a smoother ride, I think, is really what that is. Here's one that went in, I think this was 1963, there in Austria on one, and they say maintenance free. I don't know exactly what all that means, but that's what the report said. So, but at any rate, Australia, and some of their conclusions are very similar to some of these others that we've talked about. The quality of the track, clear and long-lasting separation, again, layered systems between the superstructure and sub, therefore you can design based on that. And investment, it's a additional investment, obviously, so many euros there, I guess. And then obviously on branch lines you wouldn't probably be able to justify that. But it's in other words, the way they review it is it's an additional investment in quality, then pays back its cost and so forth, and on and on. So these are some of the findings from Austria. And this is the very latest I just got from Dr. Veet over at the University of Graz. But asphalt layers form a standard element, all new high capacity and high speed lines in Austria. The one on the right here, I guess, has been in since 1991, and here's some others over there that have been in. All right, a couple of slides of concluding comments here, and then I'll be finished. The majority of the railroad track beds and roadbed designs in the U.S. basically evolved over a period of time. I don't think there's any question about that, based on later on empirical measures for that. Essentially all granular support layers. Periodic maintenance, surfacing of the track is necessary, has been for 180 years, to maintain the required geometric features, which is the final analysis of the safe speed and so forth. Each track bed support layer provides specific qualities to the track, and combined they are a system that has to be really analyzed as a system. Computer systems can be used to design and analyze layered track sections, structures. If you can identify the properties of each layer, the thicknesses. If you have failure criteria, then you can actually predict design life or service life as well, if that's the case. Of course, Ken-Track be used here. Then if using the relative effects of various layer compositions, properties, and thicknesses or sensitivity analysis can be used. Study the effects of wheel load, subgrade support, thickness of ballast, properties of the asphalt, thickness of the subballast. All those things can be evaluated in that. Also, there's considerable interest in selected international railway agencies to develop innovative track bed structural design programs and to develop both the programs and designs and techniques, construction techniques as well for that. We've featured 3 of those from 3 countries here. And basically, the incorporation of a constituent layer of asphalt within the track structure and follow-up performance evaluations for 3 Western European agencies were highlighted. And basically, and I skipped over this to some extent in those, but the asphalt layer augments or replaces a portion of the traditional granular layer, support layer, providing documented evidence properties to the enhanced properties to the track support structure. So that's some of the concluding comments there. And on behalf of University of Kentucky and our AREMA student chapter, which is known as the Railcats, we were going to use the University of Kentucky Wildcat mascot from the Athletics Association. We were prohibited from doing that. We thought about using the Chessie Cat from the Chessie Railroad, and that's sort of trademarked too. So we designed our own unique feline up here, and that's the one you see there. So, but at any rate, I appreciate being here, and I hope you've enjoyed this. And I'll be glad to take any questions that you would like to have. How's our time running? I've never looked at a clock. Okay, that's good. Any questions? Yes, sir. Over here? Or
it strikes me that in this country, an approach like this with the asphalt subgrade, to do that, to retrofit track to do that, you essentially have to scrape the track to the subgrade. Right?
That's very hard, very expensive, and almost prohibited.
I'm wondering if there's been if anybody's looked at, or you aware of any efforts to look at using that technology selectively, like transition areas, crossings, areas where there's been washouts, because obviously the granular system is probably less expensive and works fine probably in 90% of your applications.
That's right.
You are going to have problematic situations where it seems like it might be worth trying to implement something else. I'm wondering if anybody's looked at that.
Okay, did you pick that up? Yes. Okay, the question was, how about in the United States using this on selective applications, assuming that the track is in the way and obviously you can't pave as you normally would, and that's true, and that's what has happened. I purposely didn't cover any of the U.S. applications because I just didn't have time, and I wanted to highlight some of these in Europe, although which is new construction, essentially all of that. Some of the Austrian is retrofit. But that's the problem. But it is being used. It's pretty much a standard now as an example for wheel impact load detectors. In fact, I've been on a couple where they've actually retrofitted two existing ones, drug the track out of the way, paved 500 feet, drug it back on later in the day. And the primary reason was with the variability in the subgrade properties, they were picking up differences in impact, but those differences are supposed to be due to flat wheels, not undulating and various modulus subgrade, and that was the reason for those. And bridge approaches, road crossings, special track work, turnouts, diamond crossings. It's been used for a lot of those tunnels even. I've been on several tunnels too. So, but it's selective where the problems are the most severe, and then where the economics can prove beneficial there. And we've done some economic analysis. The problem is every site is different. Every site is totally, early on, we actually, on a tunnel entrance, the payback was in 4 months, if that makes any sense. And really, that was the truth. 4 months was the payback. But nonetheless, on some it's not quite that dramatic, of course. But that's the situation. But you have to analyze each, and based on the traffic and you know what the payback is. But obviously, it does increase cost. And another thing we've worked with that gets around some of these logistic problems. One of the biggest problems, and even in these short sections, is being able to get hot mix asphalt out there when you want it, the quantities you want, and keep it hot. So the solution there is go to a material that doesn't require to be heated, and those are some of the newer polymerized ACs. At least Metrolink calls it AC to, out in Los Angeles, we did several of those projects to distinguish it from cold mix, which doesn't have the best reputation. So these are polymerized ACs, but they work much differently. And there's pretty good indication that those may have some real benefits, particularly in isolated locations where all those can be stockpiled ahead of time, and probably has properties that would be the pressures we're talking about now. All of these pressure measurements were on good track, and they're very low. But at those pressure levels, 15 psi, 20, 30, you know, those are very, very low pressures. So it's not that you have to have a real high modulus or extra strong material down there, but probably it's a little bit better to have a little more flexible, resilient material that'll give and take a little bit, and prolong any fatigue cracking that might happen, and actually its strain energy is much higher, so it can strain more without cracking. And then the other thing is that the oxidation level down in the track structure is almost non-existent, and we've been able to show that. There was an article, 2008 ARIMA conference paper that documented that sort of thing on a number of cores that we had taken over a period of time. So there's no ultraviolet oxidation or temperature extremes, so that's part of it too. It's probably a little more than you asked for, but okay. Okay, let me give Tim a speaker here.
Thanks. Jerry, in the French case history, you mentioned there are installed accelerometers on the sleepers. Do you have an idea or remember what the range of accelerations measured and the change with time?
No, and I don't think that detail is in there. We have one report that we got in the last 2 or 3 weeks, and I don't think that detail is in there, what they're talking about. I'm assuming it's very, very low. It would have to be. These are concrete ties. As they said, the deflections were 1/3 of the allowable, so that range is pretty small, probably. Yeah. Might, you know, maybe in millimeters or less. Okay.
In addition to not being cost effective for the branch line, is there any major disadvantage or limitation or challenges of implementing the asphalt?
Okay, it's primarily economics. On the branch line, you really don't have enough traffic and enough damage many times to justify the extra cost. I think it's more of an economic decision of the higher performance. And the branch lines have lower speeds, and you don't need that high geometric, conformation to that. So I think that's what it is. Not that it won't work, it's just not economically feasible. The higher the volume of traffic, then the more economically feasible any upgrade or any higher price will be. So you can amortize that over more traffic. And on the lines that are higher capacity, whereby having speed restrictions and slow orders really impact your operation. So it's more from an operations economic standpoint than that it won't work. I think that's what they meant by that. That's the Austrian you're referring to. Yes. Okay.
Other questions?
I don't know who's in charge here. Okay, we'll go back. We got another one on the front here when you get finished from.
Early in your presentation, you were referring to minimizing displacements. Just to
Minimizing what?
Displacement within
yeah.
your track system to help reduce degradation. And I believe in the literature there are specific recommendations of what that displacement should be. I was curious if your experience has shown what displacement or what stiffness is optimal for this type of track structure.
And now you're talking about the track modulus measurement or actual deformation in inches or both. Well, typically
both.
Typically it's about a quarter of an inch for wood ties. What we've measured is about a quarter of an inch deformation, and that'll correspond to a track modulus somewhere around 3,000, maybe 4,000, 3 to 4. Now concrete tie is much higher, but we have measured those with LVDTs and just the regular static track modulus test, and around 3,000, something like that, 35. It's not very little, if any, and actually the French, as they said there in one of the conclusions, that the stiffness was not abnormally increased. That's what we, from comparing that with a very good ballasted granular subballast track, very little difference the asphalt adds. It really doesn't increase the stiffness very much. Now, if you put the ties directly on the asphalt, that would be another situation. But with the ballast layer in there, then we haven't found very little increase in stiffness. But what will happen, and what does happen in my opinion, is that stiffness will be consistent, homogeneous over a longer period of time and not degrade. So I think that's the key there.
Have there been case studies, since you're talking about this homogeneity, which since ballast is non-homogeneous, with an increased homogeneity of your subgrade, has there been any case studies investigating the effect or the increased performance of the tie life or rail life?
Not specifically, although I have observed on some road crossings that had been in 15 or so years where the surface finally deteriorates. And believe it or not, the ties look like they went in yesterday. You know, they're still absolutely worn practically nowhere whatsoever, but they stay dry and stay smooth and level. So that's a long-term thing, and that's certainly something that could be looked at over a period of time.
I got one,
Yeah.
Jerry.
Yeah.
I think I recall seeing it. Maybe it was in France or maybe it was Italy where they considered both asphalt and concrete and went with asphalt. Why
That was years ago when that decision was made, apparently, and I'm not sure what the solution was. I suspect some of it probably had to do with the expediency of construction, which asphalt is, plus the fact down in the track structure, concrete's pretty brittle material, and I'm not sure that would be desirable. Probably from the standpoint of crushing the aggregate or maybe just basically the bending strength and the fact that it's very rigid type material. I suspect that is the reason for that.
Jerry,
Yeah. Oh, yeah.
There's been a lot of development of cold mix in the States in the last several years with both foam and engineered emulsion. And with those materials, you can use a lot of borderline aggregates, et cetera, You're not into the high-level QC, QA stuff that you have with conventional high-type hot mix. And I was wondering, is the economic advantage there something that's worth pursuing?
Could very well be.
Yeah.
Absolutely.
But those mixes are doing quite well. We've had great success with those. And it's really becoming a hot item for full depth reclamation of old flexible pavements. So,
Right.
yeah.
Could very well be. There have been instances where, particularly out west, where some local aggregates have been used with an asphalt mix on new construction that were not suitable for a subballast, all granular subballast, but were, when you encapsulate it in the asphalt, still perform and could be used. So that's another example of using locally available.
You can use cold mix plants on site too.
Oh, yeah.
Get rid of a lot of, heavy duty transportation.
And stockpile, actually, we've actually done some tunnels where the stockpile has started in the evening, and we've added during the night. And in a big mass, it takes it a long time to cool off, and then you pull out of it the next morning, and that's worked very well with hot mix. And it's still, you're really trying to put in a super dirt is what you're trying to do. So that's really is applicable, particularly in some of the tunnels. Basically, in the tunnels, most of the problems is due to the floor gets undulations in it, so all you do is go in and smooth it off, and then hopefully you can establish the drainage and keep the ditches free and let the water drain out, even though you can't prevent it from getting in. So that's been the solution on a number of those.
We've got a couple of questions from our online participants.
Okay.
So the first one first compliments you on your talk, and then says, in the late 80s and early 90s, fabric was the cure-all. Can you comment on this?
Well, that's, I'm not sure fabric was always put in properly. We have, on a lot of projects, we have found fabric down in the track. It generally looks like Swiss cheese. I suspect a lot of that was damaged even when it went in. And I'm not sure always that the fabric had an outlet for the drainage. And it gets in a bowl, and it actually traps water probably. So I think early on, a lot of the applications with the fabric, probably the installation, could very well have been the problem of getting it installed properly from that standpoint.
And we have another, I don't know if it's a comment, or maybe it's a question, asking if you can undercut in an asphalt layer.
To my knowledge, it's never been done, nor has it been necessary. There's no way, I'm not sure the undercutters will cut through it, so I don't know, unless you could get underneath it, but I'm not sure. You could undercut maybe, well, if you had foul ballast, but that's not going to develop, so I don't think, or to that extent, that you need to be undercut. Yeah, Earl.
Jerry, thanks for the presentation. I enjoyed it very much. I was wondering if you could elaborate on the asphalt HMA underlayment you use at the bridge approaches or some track transitions, like how, in your experience, you found the advantages maybe in the field that you observed.
Yeah, of course, you get settlement typically, particularly at open deck bridges, which are pretty rigid, and then the track is constantly settling and raising, and of course you get increased impact as you come off the bridge onto the approach. As you go onto the bridge, you hit the bridge, and so it gets impacted somewhat from a longitudinal direction. So those are the basic problems. The idea is, one is to keep the water out from the surface, to drain the water, and which I think asphalt contributes to that, and then it adds certainly to the confinement for the ballast, so that the ballast can develop its potential shear strength by being confined from the bottom, so that it has a tendency to settle or shrink. And then, of course, the other factor is to have some sort of lateral, ideally, is to have some sort of lateral support along the edges to keep the ballast from migrating down the slope or down the shoulder. And then you can have a secure structure, which I think is really what it is. So it's basically getting better support and better confinement and keeping the moisture out and transitioning that in then back into the regular track bed at some distance. So that's, I think, is the key there.
Kind of a comment with a question, Jerry. in highways, and I'm thinking of the tollway system, O'Hara modernization on the airfield side. In Chicagoland, they've pushed asphalt recycling to very high levels, 60 or more % of recycled materials in asphalt. I would think this would be a really great application with the low stress for very high recycling rates. So one, do you agree? And two, is anybody looking at that currently?
By default, on a couple of projects I've been on, we've used recycled material because we had a problem with the asphalt plant breaking down. So, so far, I can see no difference in the performance. Again, all we need here is a little bit of adhesion or cohesion there between the particles and the aggregate, the adhesion to the aggregate to form a fairly low modulus material, and recycled material should perform very well. And on a lot of these projects, it's been a percentage of the mix anyway, which is normal, so up to 30–40% has been recycled material. And one project down in South Carolina actually was a new construction, a 2-mile bypass, and it was fully recycled material. They actually milled that up on the interstate and immediately dumped it. It was never stockpiled. It came off the interstate in the trucks and was laid out as a subballast. And to my knowledge, it has performed extremely well. And it knitted together sufficiently to form a subballast. So it's really a subballast with a little bit of asphalt in it, what it is. So that's a very good application. I don't think there's any question about it, in my opinion. It hasn't been practiced, to my knowledge, very much, but there just hasn't been the opportunity, I guess, but it could be. Any other questions? One more there.
Professor Rose, not sure if you mentioned that before, but question is, does it make any sense to transform low-volume, flexible pavements that were used for transport before into a track bed? Oh,
I know a couple of parking lots that have been transferred into actually unloading yards. Is that what you mean, to leave the pavement in place? Or it could be a pavement, but these are parking lots that have been transformed into, there's one in South Carolina and one in Kansas City, where they had an existing parking lot. It was pretty well deteriorated, the asphalt, but it was still asphalt. And all they did was added some ballast and put the track on it. And that was a yard immediately, you know, and very economically. So that can be done. And there's been some yards that have been completely paved, and all the drainage was taken off as positive drainage from the surface. No underground drains whatsoever. And then it was all sloped and handled as surface water. And supposedly there was some economics. Then the other way, basically, it had to have some under drains and this sort of thing to drain water away. So it was all taken off as surface water to drain through the ballast and on off into one corner, and then they handle it as surface water into the detention pond. So I'm aware of a couple of those that have been used. But again, these are site-specific. A lot of applications are site-specific, but that's a possibility. Or if you have an abandoned highway and you want to turn it into a railroad, or certainly on a scenic tourist line, something like that, I guess you could do that too. But that should work. You know.
Thank you.
Okay, a couple more over here. Chris is getting some exercise here.
I'll be very quick. Usually, slab track is installed in tunnel or in viaduct. Do you think this technology can help installing slab track elsewhere?
Okay, I didn't quite follow your question, so just repeat that again.
Yeah. Slab tracks are usually installed either in viaduct or in tunnels. Do you think asphalt can help installing slab track elsewhere?
Oh, slab track, okay. It could be installed directly on it as a number of the concrete tub crossings now are being placed directly on asphalt without any ballast at all. And I think that's a possibility, and I don't see why slab track couldn't. It's a ballastless section, and it could certainly be the layer under the concrete. And it could be designed. I mean, structurally, you could design that. I mean, you know your concrete, you know your asphalt, whatever's underneath it, you could actually design that, and even from the fatigue or the failure, you could design that very well and analyze it. Yes, sir. Another.
I have a question. This is where they explained one of the types of the design where the layer of asphalt is placed on top of ballast. But in Germany, they opt to use asphalt on a ballastless track bed. How does that still serve the purpose?
Okay, now they do a lot of, it's sort of full depth. I did not include the German activity. They have some patented systems over there where when they lay the asphalt, they actually have a center curb in it for the ties to fit over. Okay, the center of most of those are 2-block ties, and that is the design there. It's a slab track without concrete, and it's used. Now the ballast or the granular material is under the asphalt. Probably more of a sub-ballast type material is under the asphalt, and they use that a lot, particularly in tunnels, and even have a rod that actually is drilled down through the center and into the asphalt to give it a little bit more lateral stability as well. So those are used in Germany. I'm aware of those. I did not include that today. I just didn't have time. But it's in some of our other publications that are on my website, the German activity and what they do, if you're interested in reviewing that.
Well, we have a small token of our appreciation for your
thank you.
presentation. Your LTEC mug.
All right.
So,
very good.
Again, thanks for a great
Thank
seminar.
you. You're welcome. Very good. Thank you. Turn this off.